So I was going to spend about an hour talking to you about what's going on, less than 2 hours drive from here, which is quite amazing. I thought it was going to take me about 5 hours looking at the map. But so just in the East Bay over in Livermore, there's the world's largest laser facility, and it's the world's largest by about a factor of somewhere between 50 and 100. This is significantly larger than anything else in the world, by a long shot. It's a few $1 billion worth of investment by the US government. And as Luke said, it's the star piece in the new Star Trek movie. So, what more could you want? So I'll split the talk into 3 parts. I'll tell you a little bit about the facility itself and why it exists. It turned on in 2009, and it's been ramping up over the past 2 or 3 years. I'll tell you about where it is now and what its mission is. And also my program, which is to make use of the output of this facility to produce a source of clean power. If we ever get there, I'll tell you about that at the end. I should say, feel free to ask questions throughout, or at the end, it's your call. But the basic purpose of the facility is to try to answer this question. Could you replicate here on Earth what goes on at the center of the sun? Produce, not using gravity, but using a large laser, produce high enough temperatures and pressures and densities that you can force matter together at the atomic scale and convert hydrogen into helium. And there's a number of reasons why you might want to do that. It's fun. It'd be a nice thing to do. So, which is the 95% reason. And if you do it, you can actually study what goes on at the center of the sun and in supernovae on the surface of a white dwarf and so forth. So there's a lot of pretty cool science you can do on this facility. The real reason it was built was that if you can replicate these kind of conditions, you can mimic what goes on in the heart of an operating nuclear weapon. And so you don't have to go and explode those devices underground in Nevada anymore. You can use experimental facilities like the NIF, coupled to high-performance computing, to figure out whether the stockpile is safe, secure, and reliable each year for the president. And then finally, if you can get it to work at scale, you can use this as a power source for carbon-free and emissions-free electricity and energy generation, which is my program. So this is the story I'm going to tell you. Now, there's a good reason that the sun is 93 million miles away. It's giving off a fair bit of power. So we're not proposing to build a sun. We're proposing to build a sun that's significantly smaller. The reason you would want to do this from an energy perspective, is pretty profound. There's only about a milligram worth of fuel in the system at any given point in time, and you're trying as hard as you can to burn it all. So there's an inherent safety there. There's nothing that can run away, as you would have, say, in a gas plant or a nuclear plant, and produce an explosion. It uses water, not turtles. I've been asked the question before. It actually uses water as the fuel, or at least part of water. One part in 6,000 or 7,000 of any form of water is deuterium, not hydrogen. It's not H2O. It has D2O in there. Ever since about a minute after the Big Bang. So you can extract the deuterium from water, combine it with tritium, and I'll come back to that later, to produce a fuel source that should last for a few million years, which is probably long enough. And then, because everybody has access to the water at the scale that's needed, and I'll talk about that later, you don't have to go to the ends of the world to find your fuel source. The nature of the energy source is very much baseload in character. The NIF is built at a scale that it provides energy output, as designed, that would provide enough electricity for about 1 million people. So about a gigawatt's worth of power. So enough for San Francisco or cities of that scale. There's no noxious emissions like NOx or SOx. There's no carbon emissions. And it's built from industrially attractive technology, and I'll come back to that. And you don't have a long-lived waste storage disposal problem, say Yucca Mountain. There's only one small problem, and it's never been shown to work. Never stopped us yet. So the purpose of the NIF is to try to tick this box here that doesn't exist. Can you actually get it to work after 50 years or so of trying? And so, so what does getting it to work mean? Well, if you look at the sun, you've got to get to about 10 to the 11 or 10 to the 12 atmospheric pressures. This is incredibly high pressures. Hundreds of gigabars of pressure at the center of the sun, and the temperatures are tens of millions of degrees. So this is way outside of our normal experience in terms of temperatures and pressures, and the densities are a few hundred grams per cc. So many times 10 to 100 times the density of lead. So non-trivial conditions. And the way to do it, we believe, is not to use gravity, which the sun uses, and the sun's what, about 1 million miles across, something like that. To produce that in miniature, about 1,000th of an inch or so, using very high power lasers over very short periods of time, billionths of a second, and these 1,000th of an inch scales, to create actually slightly higher temperatures, slightly higher pressures, slightly higher densities than the center of the sun, to make the reaction go incredibly quickly and get enough energy out to provide either scientific information for studying solar physics, for providing nuclear security information for the stockpile, or for energy output. The fuel itself is about, as I say, 2 millimeters wide. It gets compressed to about 1,000th of an inch, and it's held inside an oven that is about 1 centimeter or so long. And I'll show you movies of how this works in a minute. And this is the fuel pellet, that when energized by the laser gives off about 30 or 40 kilowatt hours worth of energy. And that's enough to heat a family home for a day or two, from a tiny, tiny pellet of fuel. So if you actually do the maths, then each one of us would need about 2 or 3 drops of water per year for your entire energy needs. It's an almost inconceivable fuel source. Many times the energy output from a fission reactor, and a few million times energy output from a chemically burning fuel like coal or gas or oil. It just has to work. So the story began actually way back in 1960. This is all a California story, interestingly. As you can tell from my California accent as well, I'm part of this story. So back in Malibu at the Hughes base in 1960, May of 1960, this guy, Ted Mayman, produced the world's first laser. And it's very much like the NIF in concept. You have an electrical source that discharges through a fluorescent tube. In this case, it's a bended fluorescent tube. That discharges white light, and the light gets absorbed in a thin, in this case, ruby crystal. In the case of the NIF, it's large slabs of glass, but the concept is the same. And Mayman got the device to work in May of 1960. And a few days later at the Livermore lab, just up the road, a few miles up the road, and this is what it looked like in 1960. You can still see the the runway, the remnants of the base there. This guy, John Knuckles, who was subsequently director of the lab, looked at what Mayman was doing and figured out that if you could get laser light to work, and what laser light is just a way of getting energy and compressing it in time, so it's a few billionths of a second in time scale, and compressing it in space, so you focus the energy down, then you could get very high powers and very high power densities. In the case of the NIF, the power is about 500,000 gigawatts. And to put that into some context, the entire electrical grid in the US is about 400 gigawatts, and the NIF is 500,000 gigawatts. But of course, it only lasts for a few billionths of a second, so the lights don't dim when you turn the system on. And this guy, Knuckles, figured out, well, if you get those laser systems to work, then you could heat up matter to very high densities and temperatures. And this is trivializing it, but this is the basic recipe. Extract the deuterium out of the water and combine it with tritium that you actually breed within the power plant itself, and raise their temperature to a few million degrees for a few billionths of a second in order to get the atoms to bond together at the atomic scale and get the deuterium and tritium to bond to form helium and a neutron. And the neutron is used to carry off energy, heat up a fluid, water or something similar, and then drive a steam turbine. So everything after the energy production is pretty conventional. You just have to create a very clever oven. So this is how it works in movie land. You've got this centimeter high gold can, at the center of which is your fuel pellet, and the fuel pellet is actually a hollow spherical shell, and the fuel is held in a solid form in the inside surface of that sphere. And you put the pellet in your oven. We call it a Hohlraum, just following a German convention. And over a few billionths of a second, the laser light irradiates not the pellet, but actually the inside walls of this gold can, the oven, to heat it up to high temperatures, to create a thermally uniform environment. And it heats up all the way from red hot to white hot. In this case, X-ray hot. It's about 300 eV, 400 million degrees. And the outer skin of that pellet vaporizes to high radius. And just following Newton's laws, the inner part, the fuel, goes inwards. And if you get it right, the fuel can compress on itself, compress from all directions in 3 dimensions, and compress on itself to get to very high densities, very high temperatures, very high pressures. So that was the concept way back in the 60s and the 70s. And it's taken decades of laser development to get to the point where finally we have a laser system, we believe, that is large enough in order to be able to enact that at a scale where the fusion energy output is more than the laser energy input. It's a net power. So back in the 70s, there were major technology developments in the laser world, factors of 10 jump every few years, and then in the 80s, a facility was built. These are all at the Livermore lab, which throughout this period has actually led the world, very interestingly. In the 80s, there was this laser program called NOVA, and it was combined with a classified program downhole in Nevada called Halide Centurion, where the NOVA laser was looking at how laser light can be absorbed and heat up matter, and the Halide Centurion program was looking at how fusion can happen at large scale, and combined the two programs together to design the NIF facility, to figure out how big a laser, or actually how small a laser do you need in order to get this to work. So this was designed through the 90s and built through the 2000s and turned on in 2009. And it involved, of course, not just the Livermore lab over here somewhere, but about 3,000 vendors across the US. Many, many academic institutions as well. There was about $2 billion worth of industrial investment, involvement rather, in the US. And I think only North Dakota and who else? Mississippi missed out for some reason. So there we go. Don't know what they did wrong, but don't go live there. So, all right, so here's the NIF. It turned on a few years ago. It's about 400 feet long, just to give you your feeling of scale size. So it's like a stadium, a football stadium, by which I mean proper football, not soccer, I guess, as you would call it. It's about a stadium size, and most of which is the laser itself. About 300 feet long, 200 feet wide is the laser system. And the pellet of fuel is held inside a target chamber in this side of the building, and I'll show you more about this in a moment. If you take the top off, you can see it more clearly. Here you have two laser bays, and it's not one big laser, of course. It's, in this particular case, 192 separate laser beams, each one of which is about 1.5 feet wide. It's a square laser beam, running the length of this 300-foot long laser bay. And it works very similarly to Ted Mayman's laser back in the 60s. You take energy off the grid into these capacitor banks, these red units here. The capacitors discharge into a series of amplifiers, and I'll show you more about this in a moment. They discharge their energy into a flash lamp, a fluorescent tube that gives off white light. The white light is absorbed in slabs of glass that have a lasing medium inside them, and the laser light bounces back and forth, extracting the energy out of that optical battery, the laser gain medium, directed to the top and bottom of this 10-story building, and then directed down into this 30-foot diameter vacuum chamber, at the center of which is the fuel. Right, so to show that in movie space, and I'll show two different movies to show, the laser light starts off as a fiber optic, gets amplified up into the main laser bays and bounces back and forth 4 times. We'll see this in more detail in a moment, till it extracts out the maximum energy, goes to the top and bottom of this building, and then focuses down onto the fuel. What could possibly go wrong? All right, so to show the real movie, would last about a microsecond or two. So I'm going to slow down time and actually show what happens inside this facility as it's operating. So here the guys are actually counting it down. And I'll come back to the main laser train in a moment. They're just energizing those flash lamps. The birth of the laser system are these fiber optics, telecom style technology. You could probably fit this whole thing in your iPhone at the moment, but these 2 fiber optic bursts are sent to the 2 laser bays. There's a factor of 10 to the 9 amplification in a preamplifier to get to about the joule level. So it goes from nanojoules to joules, then goes up into the main laser train, where you can see it's grouped into these bundles of 2 wide and 4 deep bundles of 8 laser beams, moving at the speed of light, of course, each one of which is about 20 feet long and 1.5 feet wide, because it's about 20 nanoseconds long. And it goes to this purple laser glass, this neodymium laser glass, that's energized by those flash lamps, extracting out energy from the laser glass, until at some point it reaches its design level. And this group of 8 beams is joined by its neighbors to form a cluster of 48 beams. Another set of 48 is alongside, 96 on the far side of the room also. The light bounces off to the top and bottom of this large 10-story building. And at this point you can see some laser beams are racing ahead of others. So a set of optics are used, and these are meter scale optics, to time up to a few trillionths of a second. The laser light is actually converted from infrared to ultraviolet, so it gets absorbed efficiently. And now we're on the inside surface of this 30-foot diameter vacuum chamber, at the center of which is the fuel, and you've seen this already. The laser light comes from the top and from the bottom, hitting the inside surface of this gold can, heats it up to a few million degrees, and after about 15 billionths of a second, the pellet starts to ablate outwards, vaporize outwards, so the fuel goes inwards following Newton's law, and if you get it right, you get significant fusion energy output. So this whole process of turning the laser on, focusing it down, getting the pellet to implode and give up fusion energy has now been going on for about 2 years. And steadily the progress has been going up and up, but not yet to the point where the fusion energy out is more than the laser energy in. So it's not yet a net source of power. And that's the objective over the next year or so. So let me show you a few images of the facility then I'll get on to what we're doing with it. So this is the preamplifier, taking the fiber optic energy input, raising its energy by about 1 billion times, 10 to the 9 times. So you get about a 1 joule laser system out. And then it gets directed to the laser glass itself. And the lasing medium in this case isn't that small sliver of ruby crystal that Ted Mayman had. You know, these are meter scale glass slabs, you know, a few hundred tons worth of glass in order to host the neodymium that acts as the lasing medium. And this was actually produced by 2 companies, a German company and a Japanese company on the east and west coast of the US. And actually a new manufacturing process for glass had to be invented by the project in order to get the high enough purity and the large enough volumes over the timescales that were needed. So we went from a batch mode production to a continuous flow, continuous pour, continuous melt process, working with these industrial partners. And this was a great exchange between the physicists at the lab and the industrialists on the factory floor, exchanging over about 3 or 4 years, about $100 million worth of investment together. So that laser glass is held in amplifiers that sit to the back end of this laser bay. This is the 300-foot long laser bay, one of 2, and here you can just see for scale size, one of the livermorons, as we call ourselves, and you can see the laser beam tubes here, each of which is about a couple of feet wide or so, 2 wide and 4 deep. And those laser tubes, those beam lines, are held high above anybody's heads, mainly to make sure that students can't get to these facilities and fiddle with them. Quite seriously, if you go anywhere else in the world and see a laser lab anywhere, here at this lab and anywhere else in the world, you will have benchtop scale laser systems with optics, and the professors and students are lovingly coercing and tuning and pleading with the laser to work. Whereas this was designed to act like a utility, to have 99.5% availability and reliability, and be robotically maintained rather than student maintained. So it's not a very good teaching facility, but it is a very good production facility. So it's held high above everybody's heads to use pretty industrial warehousing units that robotically mate with the facility to extract or insert optics as they need replacing. So I said that the laser itself operates in the infrared. It's very difficult to get a laser to operate outside of the infrared, in fact, as I'm sure many of you know. But there are techniques to convert infrared light down to visible and ultraviolet. And the technique that's most often used is using a nonlinear optical property whereby you can send very intense light through a nonlinear crystal, and the crystal actually combines 2 photons together to get 1 higher energy photon. So in our case, we would add 2 infrared photons together to get a green photon, and then a green and a red photon together to get a blue photon, or 350 nanometers. But because because the beam size is large, we need large crystals. Normally you would use conversion crystals that are an inch or so. Here you're needing 2 million carats of crystal. It's not very good for your fiance because it does melt in rainwater, this particular crystal. It's potassium dihydrogen phosphate, basically fertilizer, but grown as a crystal. And actually, again, a whole new manufacturing technique had to be produced for these systems because they took so long to grow. You start from a seed crystal, as you can see here, and then grow around it. And it was actually only after the fall of the Soviet Union that a woman at Moscow State University was found who had figured out how to grow these crystals quickly. She was ported over to the lab. We partnered with a company in Ohio to grow these, at bulk. Amazing systems. So then finally the laser light gets focused down into the target chamber. This is the 30-foot diameter chamber. You can see holes cut out in the top ring and blanked off on the bottom ring to let the laser light in. This is as it was being craned into the facility. And every time I look at this photo, I wonder what this guy with a piece of string thinks he's doing. But you just got to wonder, haven't you? And actually, they had to get one of the world's largest cranes up from the Nevada test site to get this system in. And it was lowered into the facility and a concrete shield wall built around it, in the expectation of fusion output. And this is what it looks like today, or at least a couple of years ago. You've got now shown in blue the 30-foot diameter chamber, and the laser beam lines coming from the top and from the bottom. And if you do go and see the Star Trek movie, this is the engine room of the Starship Enterprise. This is an amazing. It looks a little bit better in the movie as well, I can tell. So, and again, just for scale size, here's Captain Kirk or somebody. Who knows? All right. So how are we? So this, that's sort of the whistle-stop tour of the facility itself. Let me spend 10 minutes or so talking about how we're doing, and then talk about where we're going after that. So in terms of how well the laser facility worked, this was a journey into the unknown, big time. The laser systems that existed around the world prior to the NIF were down here in the bottom left corner, about 30 kilojoules, about 30 terawatts or so of power. And we had to get up to about 2 megajoules, 1.8 megajoules, and about 500 terawatts of power. And so we actually added one of these Nova or Omega systems, or their equivalent, every week, continuously for about 3 years in terms of energy addition to the facility. You can see the facility was turned on relatively gradually over 3 years until about this time last year, it reached and somewhat exceeded its design point. And the only way this could have happened is through a very major material science breakthrough that happened over the course of the construction project. But if you go back to these facilities, and in fact any other facility in the world, even today, and ask, how will optics be damaged when intense laser light hits them? And it turns out there's, some of that laser light, of course, is absorbed on any optic that gets hit by a high-power laser. And at some point, the optic gets damaged. And if you look at where the state of the art was, as the facility was being designed and concrete, was starting to be poured, here's a curve of how many damaged sites would appear on each optic per centimeter squared as a function of the operating regime of the laser. And this blue envelope is where the laser is being operated. So you can see that if we used optics that existed during the construction project, or in fact anywhere else in the world at the moment, on each shot you would get about 10 damage sites per square centimeter. And there are hundreds of optics. Basically the first shot kills the whole laser system. $3 billion later, you're a bit disappointed. And so there was a process where, again, the molecular dynamic calculations people were working all the way through to the people on the factory floor, working through what actually causes damage, and it turns out to be subsurface defects. How can you reduce those subsurface defects, and how can you mitigate what is residually produced after the production line? And where we stand at the moment is the green curve. So on each shot you're getting, a hundredth or less than that, a few thousandths of a damaged site per square centimeter per optic. In other words, you get about an optic per shot that's damaged. And we're hoping to go over the next year or so to a position where effectively we have damage-free systems, even though this is in a fluence level that surpasses by about a factor of 10 anything else in the rest of the world. So everybody else would be limited to about 200 kilojoules. So this is about an order of magnitude leap thanks to the material science understanding of the optics themselves. All right, so that translated through to performance. So about this time last year, between March and July, the laser reached its energy and finally its power requirements and was ready for its full fusion attempt. So we've had about a year or so of getting to fusion. This is just the inside of the chamber to follow the story through a little bit more. This was actually the front cover of National Geographic about a year or so ago. The poor guy cleaning the inside of the chamber, I guess. And at the very center of the chamber is the fuel. And the chamber needs to be this large, for a few reasons, but the principal reason is that the energy given off by this pellet of fuel, is so intense that the wall, if it were much closer, would be damaged. And so what happens is, we put the pellet of fuel at the center and then use various diagnostics to look at what's going on in these few billionths of a second and on these very small spatial scales. So for example, this diagnostic here is the world's fastest movie camera. It takes snapshot images, each of which lasts about 80 trillionths of a second. doesn't take many images. It only takes about a dozen images, but nevertheless, it's pretty useful when you're looking at how that pellet implodes. Can you tell whether it's imploding in a round fashion or not? And there are 50 or 60 or so other diagnostics looking at what's going on at the center of the system. This one, just because it's in the photo, this actually looks after the shot. It's a robotic arm that comes in with a camera on the end and looks up at every single optic and figures out whether it's been damaged or not. So the governor, Schwarzenegger, when he came down, he loved this thing, the robotic arm that goes in here. So this has a camera on the end of it, so we thought it was better than his robotic arm, but there we go. All right, so who was involved over this process? As well as the Livermore lab, it's a bunch of other Department of Energy, NNSA labs, universities like MIT, Rochester, and so forth. And the main work over the past 2 or 3 years has been installing these new diagnostics and installing the infrastructure to be able to do these fusion experiments. And in terms of academic use, there's, 70 or 80 universities in the US, and now also Europe and Japan participating. And, as well as the energy program and the nuclear stockpile program, the kind of physics you can do on this, if you're an astrophysicist, is pretty exciting. Figure out how does supernova actually explode, how do you create the heavy elements that make up, much of the world around us, all the way through to the most extreme events in the cosmos. How do you get these extremely high energy cosmic rays produced? Basically, nobody knows. Through to looking inside planets. At the moment, if you look at the planetary models, they tell you that Jupiter and Saturn have a difference in age of about 1 billion years, which can't possibly be true. And so there's something wrong with the model. And so over the past year, we've actually gone to the center of Jupiter and then subsequently to the center of Saturn to look at what goes on in the center of those planets. Of course, not in reality, just here, here in the lab, up in the East Bay, to figure out, what's wrong with those models. But the main program, the main reason the NIF was built wasn't to do any of that stuff as such. It was to get to ignition, to get to the point where that fusion fuel starts burning and you get energy output. And it's a 4-step process. You have to build the laser, you have to commission the so-called hologram or oven, heated up to high temperatures, commission the capsule so it starts imploding in a nice uniform spherical way, and then get the fusion fuel to light. And so this whole process started in 2009, and here just showing you some real data to give you a feeling for what data looks like from these facilities. This is a snapshot image from that movie camera. The snapshot lasts a few tens of trillionths of a second, and the spatial scale size is about the width of a human hair. It's about 100 microns. And what you're looking at in the false color are the X-rays, the energy being given off by the fusion fuel. It's not giving off so much fusion energy that it's net break-even yet, but it's still giving it off. You can see on the first shot, which was 2nd of September 2009, this pellet of fusion fuel was not imploded in a round fashion. It was very pancaked, very squashed. And so over the course of a few days, there were changes made actually to the wavelength of the laser by a few angstroms to get it to go from a round state to a square state to a flat state to a square state to a round state. So at this point, everybody was very happy. Thinking, oh, what's the problem? We can make this work. So, 3 years later, we've got from the point of these implosions, which were about a factor of 60 away from performance, ignition performance, to about a factor of 2 or 3 away. So we're not quite there yet. It took about 1.5 years, 18 months to install all of those diagnostics and the other tritium and cryogenic infrastructure to make the real system have the environment that it could be fielded. And so where are we now? We've got a system where the laser works above spec, the hologram actually gets to the temperatures that are needed, and the implosion looks okay but not great, but it isn't quite there. It's only 150 billion atmospheres. It needs to be 350 billion. So it started off at about 5, it's got to 150, we need to get to 350, just to show you where we are. And just to show you, this is a real movie of the data of the fusion energy coming out as a function of time. So this is lasting, what, about 300-400 picoseconds, so 300-400 billionths of a second, trillionths of a second. And what you're seeing is the fusion fuel giving out energy as a function of time. And you can see it's sort of round, but not exactly round. And so just plotting that on a log scale, we sort of started off down here, 10. We're here in 2012. We've got a factor of 2 or so jump to go in pressure space, or about a factor of 10 in output. So we'll see. We're not convinced we can get there. We think we can, and we shall see. And so the purpose of many of the programs now is figuring out, given that the progress has been pretty good so far, and that the final factor of a few looks achievable, what should we do when we get there? Okay, I won't bother with this. Let me move on. Boring you already, Bassam. That's not good. So let me just tell you what's going wrong. Why can't we get that final factor of 2? And then I'll talk about the way forward. So this is a photo of the pellet, that fusion fuel pellet. It's about 2 millimeters wide. And it's a plastic pellet on the inside surface of which is this deuterium-tritium fusion fuel. So once the laser beam hits the oven around it, the wall around it, gives off X-rays. The X-rays hit the outside surface of this capsule, starts to get hot, the outside surface ablates outwards, and the fuel goes inwards. So in the very first nanosecond, the first billionth of a second, the energy, X-ray energy is heating up the outside surface of this pellet, and it's reasonably uniform. This is uniform enough, it's nice and round. But as time goes on, this is just showing you the quality of the data or lack of quality of data. You can see the dark shell here is the fuel as it's going inwards and going inwards even further. And you can see if you've got a good eye, this isn't quite round, this is squared off. So that by the time it gets to its final imploded state, if I blow that up, even though in emission it looks round, the actual fuel is not what you would call round. That is distorted, heavily distorted. You can see it's diamond shaped and it's split into lobes. So there's something going wrong in these early stages that's introducing a distortion. And it turns out its percentage changes to the length of this oven can make dramatic changes to the shape of that implosion. And that's what we're looking at the moment. Over the last few weeks, next few months, making tiny percent level changes to the performance of the design of the fuel in order to change the performance by factors of a few. And then finally, the other change, this pellet is actually held, doesn't suspend in midair, doesn't levitate, it's actually held by a few tens of nanometer thick membrane that sandwiches the pellet inside that gold oven. And if you look at the models, the codes, they tell you this should have no effect whatsoever. This should introduce no perturbation because it's so thin. Mother Nature thinks differently. And you can see these snapshot images, again, taken over about 100 trillionths of a second, about 100 picoseconds. You can see there's a very distinct cut, guillotine almost, at the top and bottom of the pellet. The sort of smiley face and sad face, or the tennis ball, depending how you want to look at it. And that seems to be introduced by these few tens of nanometer initial perturbation on the pellet. So if anybody has a good idea of how to thin these membranes down while still retaining strength enough to hold a pellet in situ, or hold a pellet in some other way, will be your friend forever. So this is where a lot of work is going on. Can we get this down to 10 nanometers or a few nanometers thick? Can we hold this in some other way using threads or strands, or even a stalk perhaps, in order to reduce the perturbation? There are other ways to get rid of this problem using the physics, but it'd be nice to get rid of it in the manufacturing process. All right, so that's the end of the second part of the story. I want to spend 10 minutes now just saying where could this go from an energy production point of view. If that system does get to the point of ignition and energy production, the NIF is of a scale size that the energy output as designed is enough to give you the fuel performance that you need for a gigawatt scale power plant, about 1,000 megawatt power plant. And so over the past 5 years or so, our lab and working with many people around the country and around the world have been designing the power plant that goes by this acronym of LIFE, Laser Inertial Fusion Energy. The inertial is in there because the way the fuel actually burns is you compress this system in space, and it actually sits there for long enough because of the inertia, the mass inertia of the fuel. It doesn't disassociate for about 100 picoseconds. And 100 picoseconds is enough for the fuel, enough time for the fuel to burn. Now, nature needn't have been that kind, but she was. And so it turns out that fusion fuel burns over tens of picosecond timescales, and the inertia of a milligram worth of fuel is about 100 picoseconds. So you win out. You win out enough to burn about a third of the fuel. And so we've been designing a power plant based largely on how the NIF works, where you have the fuel at the center of the system, identical to the NIF. Laser beams that come down and irradiate that system, identical to the NIF. But then try to design a power plant that sits around it, that looks and feels like a power plant, rather than looks and feels like a science research facility. So the requirements we set ourselves, the design principles we set ourselves at the beginning are basically don't trust any plasma physicists you ever meet, because their ability to predict the future is woefully bad. So instead, you make sure that any of your fuel that you put into the system has been baselined directly at full scale on the NIF. And if anybody says, well, I just need a laser that's twice as big or 10% bigger, just don't trust them. So, and then similarly, don't trust material scientists or technologists. Another good rule in life I've found. Such that you want to be using technologies that, wherever possible, you can point at a vendor base that will supply those technologies. And then finally, from an operability point of view, make sure you can produce a system that has high 90% availability, and wherever possible, make sure that the systems can be built off-site in the factory, so you don't need specialists in your plant. And if for some reason, when we talk to the utilities like PG&E and Southern Cal Edison, those kind of people, they don't want plasma physicists or laser scientists in their power plants. I don't understand why, but apparently they don't. And then finally, make sure that even in the worst case accident scenario, you don't have an off-site impact where you need the public to do anything. That's the design principle. So we've talked with a bunch of people from across the utility world, people who supply our electricity, whether it be from the biggest companies like Exelon or local companies like PG&E. And they basically tell us these things. Make sure that whatever you do is compatible with the existing grid. So you don't need to go away and build high voltage DC transmission lines, for example, because it's too expensive and too many people complain. Very high plant availability you've talked about. Of course, it has to be commercially attractive. Sustainability is perhaps one of their biggest issues. Use of water. If you go to a thermal plant like coal or nuclear, it uses about half a ton of water per second, which is completely unsustainable in many parts of the country and of course, many parts of the world. This talks about not having scientists in your power plant, and then the simple regulatory path, and then timeliness. That if you look across the US fleet, the US power production fleet, the vast majority of power stations that exist today will have to be retired out by the middle part of the century. And so there's a huge recapitalization of the whole industry that's needed over the next 30, 40 years. And so if you want to meet the sustainability and all of the environmental and other attractive aspects of this plant, if you're not online in the next 10 or 20 years, you've basically missed the boat. And that was just detailing that. So what we've done, we've spent a lot of time over the past few years working with a lot of companies, a lot of engineering companies particularly, putting together this power plant design. I just want to give you a feeling for what it looks like. In cartoon space, it looks like this. You have a laser that is basically derived from the NIF, and a fuel system, again, that is derived from the NIF. And the laser, of course, there's a few hundred laser beams, not just one, and it illuminates the fuel pellet and produces fusion energy, is the idea. And that energy that's given out, largely in the form of neutrons, gets absorbed in a pretty conventional thermal cycle, where you flow a fluid around a boiler. Think of this like a boiler, around a series of tubes that carry a fluid, and the fluid goes to a heat exchanger and onto a steam turbine generator unit. But at the same time, rather than just choosing water as your heat exchange fluid, which would be conventional boiler technology, you use a fluid whereby when it's irradiated by the neutrons coming out of the pellet, that fluid makes its own fuel. So the neutron hitting lithium will produce helium and tritium. So you can actually produce half of your fuel source within the cycle of the plant itself. The other half you have to go and extract out of water. The deuterium comes off-site, but the tritium actually gets made on-site if you choose lithium or lithium-bearing compound as your circulating fluid. And you use about 0.1% per year of that fluid as your fuel source. So it's a very strange engine. It operates in a cycled mode whereby every 10th of a second, 1,000 RPM, you're injecting some fuel. The fuel gets energized by, in this case, a laser. It ignites and gives off energy. You exhaust and you recycle. So very much engine-like, and an engine that you extract out 50% of your fuel as you're going along. So in numbers, it looks something like this. You build a laser that's about the same scale size as the NIF, because you don't want to speculate. You want to test this system at full scale. But you run it at 1,000 or 1,500 RPM. Something at that rate, very much like an idling car engine. And these lasers turn out to be about 15% efficient. So you need to power it, of course, but you're getting about 30 or 40 megawatts worth of laser light out. Put that into your fusion system, and the fusion is designed to multiply that energy. It's what it's there for, of course. In this particular case, by about a factor of 60 or so. So you're getting about 2,500 megawatts worth of fusion power out that gets absorbed in your flowing liquid. Turns out to be an exothermic process, so you're getting about 10 or 20% of additional energy for free just by the absorption process. So about 3,000 megawatts worth of thermal energy out, and you put it through a cycle. You put it through a Rankine cycle or some other Carnot-like cycle. So you throw away about half of your energy you've lovingly produced, and the other half gets converted to electricity, some of which powers your laser and other systems, and in this particular case, about a gigawatt goes to the grid. In terms of the power plant itself, it's about the same width as the NIF, about 100 meters or so across, 300 feet or so across, and it's a very modular system, as I've talked about. The reason we think we can put this plant on the ground within 10 years or so is basically in the expectation that NIF will perform, and then using modular components where possible to actually extract out from industry what they're already doing. So I'll show you a little movie of how this works, then I think I'll move to the end. So this is a movie of the plant. You've got a whole series of, in this case, we compress the whole laser system into boxes that are about 30 feet long. And the pellet isn't held in place, it's actually injected downwards. You can see this pellet, it's moving at about 250 meters per second. It's going through an injector system and through into the chamber. This is the 30-foot diameter chamber, just like the NIF. And when it gets close to the chamber center, it goes through a series of crossed laser beams to determine its velocity and trajectory. Now, this is a well-behaved target. You Navy guys, this is a very well-behaved target. You know what it looks like and where it's trying to get to. And so when it gets close, that system turns on the laser, and then at the very final moments, a very low-power glinting laser hits the target, scatters light of every single laser train, and makes it all the way back to the front end of the laser where you have an acousto-optic modulator, very like a lithographic system. So you don't have to have any moving parts. You can have a system that understands exactly where its target is because it's just been looked at by a glinting laser, and that defines the trajectory of each laser beam independently. And those then, of course, illuminate the inside surface of the target like we've seen before. So, so let me just run it one more time so you get it in your minds. That we modularize the system where possible, and we make sure we have no moving parts, because if you have moving parts in a system that's running at 1,000 RPM, as anybody knows who's ever driven a car, stuff goes wrong. So we try to make it, other than the fuel injection itself, which we try to make a contact-free injection system. We go through the tracking sensors. They basically determine the time at which the target is going to get there, and they also determine where it's going to get. So this doesn't have to be injected to an absolute point in space and time. It just has to get close. And then the system tells each individual laser beam where it is and when it is. And it needs to get to within about 1/10 of a millimeter, about 100 microns, in order to get accurate enough, we believe, to induce fusion. So the laser system itself, just like the NIF, is a 4-pass laser system. So you see the light going back and forth through the gain medium. This is about a 30-foot long laser beam, of which there are a couple of hundred, and then the laser light comes down. The chamber itself is the other hard bit. And you can't, like the NIF, build a chamber out of aluminum, like that big globe that you saw, because it doesn't have the strength properties that you need. So you need to use steel or something like steel in order to get the structural properties that you need. But unfortunately, if you use a conventional steel, the neutrons that hit it will irradiate the steel and render it useless after a few years, because it gets embrittled, because each atom in the lattice gets displaced from the lattice about 10 times per year. And there's only so many displacements, per atom that you can survive, about 10 or 20 or so. And also there's a second problem in that there's activation of the steel such that you end up having a long-lived radioactive waste stream, defeating the whole object of fusion. And so we designed this system instead to be a modular system of pipes. These are few-inch diameter pipes. This is the work of Bassam, and he was left early, so I shouldn't mention him at all. So this is the work of Bassam and Company, producing a pipework boiler that sits as a series of, you can see these orange peel segments, these modules that form the chamber itself, and produce it in a way that every few years, rather than every few decades, you can replace this system, and so it doesn't have to last for a few decades, it only has to last for a few years. And if you work through, it seems that a pretty conventional ferritic martensitic steel may be good enough, as long as you remove out some of the bad actors from an activation point of view. And so we looked at what are those bad actors in terms of activation. It turns out molybdenum is the worst actor, so you can take that out and replace it, say, with tungsten. But then in terms of the impurities, for the materials that we've got made at the moment, there are impurities at the part per million level that you have to care about. And so this is a stretching goal in terms of, can you make a few hundred tons worth of steel components and keep these part per million level impurities? And we don't know. That's the challenge at the moment. In terms of the raw materials, it seems that you can. We're just fabricating some products at the moment, and of course the impurities go up. And so this is an iterative process. But if you can manufacture the steel, Joe and Bassam and others have been working on various bonding and welding techniques. Here, trying to get a seamless bond. If this line weren't there, I'm sure you wouldn't be able to detect where the bond was. And then heat treating various weld processes to try to get back to the base metal strength. And some very exciting results just recently over the past few months, past year. I know, working with a bunch of guys here, to try to figure out where this can be taken over the next couple of years or so. Very encouraging results, I think. All right, then the laser system itself. I have to talk about the laser system. It's part of my contractual obligation working for the Livermore lab. Otherwise, I'll just get fired. So this is another view of the NIF laser bay. It's about 300 feet long. But actually, the preamplifier sits in these boxes. And this is the main part of the amplification system. The challenge of life is, can we fit the entire laser system, this 300 feet long, into a laser box that fits on the back of a truck? It's about 30 feet long. And we believe you can by changing out those fluorescent tubes that sit as the power source of the laser for semiconductor laser diodes. And those laser diodes have been around for about 10 years, and their performance has been at the right level. The issue has been cost. And it's because of the flat panel TV market and the laser hair removal market, where people knowingly buy lasers and burn hair off their skin. It turns out to be a few $100 million a year market. Amazing. Those two markets have brought the price of these systems crashing down by about a factor of 10 over the past 3-4 years, that we can now afford to buy these laser diodes and put them in a box to produce the power output that we need. So this is about 130 kilowatt average power box. Peak power, of course, is much higher because it's a nanosecond pulse system. All right, let me skip through this. So and this philosophy of, can you put lasers in boxes and live at high availability in a factory environment over long periods of time, was actually worked through, not for the laser fusion program, but for the atomic vapor laser isotope separation program, the uranium separation program back in the 80s, where for about 14 years this system stood operational with 99% or so availability using these robotically maintained laser boxes. All right, and here just showing one of those laser systems in action. So this is much better if I turn the sound on. Let me turn the sound, and then I'll finish. Here we go. So this is a view of we're going to see a laser beam that's about 10 centimeters, a few inches wide on a square, burning through a sheet of metal. It took I don't know what, a few seconds. This is operating in about 25 kilowatt average power mode. This particular laser system, which is a heat capacity laser, got to about 65 kilowatts ultimately. We need about 130 kilowatts for the live system. So in terms of thermal power management, it's not too far away from this system of about a decade ago. But in terms of pulse power, of course, it's quite different. So, all right, let me just move to the end. Sure you don't care about the economics. Nobody else does. I'll actually just talk about this. What else is going on in the world? I'll finish with this. The NIF laser is about somewhere between 5 and 10 years ahead of the rest of the world. As I say, it's about a factor of 50 or 100 bigger than anything else in the world. But the world is catching up, of course. The French down in Bordeaux, great place for a site visit if you want to go and see a big laser system. The CEA site, the atomic energy site down at Cester, is building a system, and there's actually a lot of partnership between the US and French governments in designing these systems. But the French, being the French, decided to do it a little bit differently. And they took a little bit longer. The coffee breaks are longer, the lunch breaks are a lot longer. So even though they started at the same time, this is coming online in about 5 years. But it looks like a good system. The Chinese have just completed a system that's about a factor of 5 smaller, and are just starting a system that will be about the same size, called Shengwen, Divine Light. We call our system the NIF. They call theirs Divine Light. It's a great name for an atheist country. So, and then who else? The Russians. Putin just gave authorization about a year ago to Sarov, to the nuclear weapons program in Russia, to build Iskra. Again, looks remarkably similar to the French system. There's again a fair bit of collaboration here. In fact, the laser systems have a lot of collaboration around the world to build a system slightly larger than the NIV. Being Russians, got to build it just that little bit bigger. So, and this is due to come online in about between 5 and 7 years, depending who you believe. So, and then around the rest of the world, the Europeans, the Koreans, and the Japanese are basically planning what to do after these systems work. So, not build their own demonstration plants, but to build the power plant, to go straight to the power plant. So, this is South Korea, of course. Japan, I was just there a couple of weeks ago, and the European program, which is where I came from, used to lead this for a while, are basically waiting for the NIF to get to ignition, or maybe laser megajoule. Yes, it's a megajoule laser. The French say everything backwards, so laser megajoule. So, or maybe these systems elsewhere. If it gets to the point of ignition, then the idea is to go straight to a plant at about 1,000 megawatt scale size. Whether that be here in the US through the LIFE program, or whether it be these guys down in South Korea, they've got a very aggressive laser diode program and semiconductor diode program. Samsung, LG, these are big companies that put a lot of money into these systems. So in Japan also, a lot of good nuclear experience in both countries also. So the ability to build these plants, given ignition, is definitely there. And the challenge for our country, as noted by the National Academies, I won't read out the text, is will we take advantage of the facility we have? And, so we shall see. We shall see. But of course, we need to get to ignition first. The immediate term challenge is get the NIF to work and get it to work to the point of ignition. We started off 2 years ago being about a factor of 60 away. We're now about 2.5 away from where we need to be. It doesn't look like there's something fundamental stopping us getting there. Difficult to tell how long it will take. Of course, it's funding dependent, so send your checks in. But it doesn't feel like a long time away. So we've been trying to plan as to what to do at that point. And with that, I think I'm over time. Thank you.
Thank you.